Good evening, everyone. Today we'll begin with the problem solving session for the week 5. So, in this week, you have covered the data analysis in X ray crystallography, in which you have looked into the diffraction patterns, what is indexing. You have also looked into different equations and Bragg's law and the relationship between these equations. Along with this, there are multiple topics that have been covered, and this was the last module related to X ray crystallography, which covered all the details related to X ray crystallography. So in this session, we'll be practicing MCQs after discussing all these topics, and then we'll also look into the current literature. And if you have any doubts, then we'll look for your doubts. Okay, so first of all, in X-ray crystallography, we need a crystal and not just a small molecule. So why is it so? So we cannot visualize molecules directly using X-ray because a single molecule is a weak scatterer. So it is not able to scatter that light enough, which could be detected. That's why we need a crystal. So most X-rays pass through the molecule without significant interactions. So the solution to this is to use the crystals for enhanced diffraction signals, and these crystals, they consist of repeated and three-dimensional arrangement of molecules. So we have also discussed in the previous session that when we say crystal, so it is composed of the smaller units, which are unit cells. And within these unit cells, there are also certain repeating smallest fragments, which are the asymmetric units. So in this case, these motifs, they represent the asymmetric unit, which are present by certain translation or symmetric operations. They are present in the repeats inside the unit cell. So this is the smallest unit which is present inside the crystal. So in this way, these crystals, they consist of a repeated three-dimensional arrangement of molecules, and the combined diffraction signal which is coming from these billions of molecules that reinforce each other, and it produces a measurable signal. So that's why we need a crystal. And in this, I have shown that if we have a single molecule, then you can see how the diffraction pattern appears. So this has appeared after the Fourier transformation. So we are not clearly able to distinguish among the positions of the atoms. But if we have multiple molecules inside a crystal, then this diffraction pattern is bit clear. So it's not blur, it's clear, and we can means distinguish among the position of different atoms present inside the protein. And this is a representation which is showing that how the crystal is mounted over the goniometer, and this is the X-rays which are passing through the crystal, and this 2 theta omega, these are representing the angles. So with the help of goniometer, we are moving the crystal in different angles so that we can record the position of atoms from different positions, from different locations. So this is how we capture the X-ray diffraction data of the crystals. So the key concept is that there is a formula given by Darwin in 1914 which says that diffraction intensity, it is proportional to number of unit cells in a crystal. So if we have more number of unit cells, then it will give a stronger intensity of the diffraction. And according to them, if we have a 100 millimeter cube of crystal, then it approximately contains 10 to the power 12 unit cells, which leads to a significant diffraction signal. And for the constructive interference in crystals, so we have also discussed last time that what is constructive interference. So if we want a constructive interference, then the periodic arrangement of molecules should be there in the crystal. So if there is a periodic arrangement, then it will give the constructive interference, and which will strengthen the diffracted waves. So this is the representation of how the molecule is present inside the unit cell, and multiple unit cells combines to form a crystal. So whenever the X-rays will fall on these unit cells, so in these unit cells, these are the lattice points. So for example, this is the unit cell which is in the shape of a cube. So in this case, we have different lattice points which are present in the corners, and in this way it will construct the planes. So in these planes, whenever the X-ray beam will strike each atom, then it will get diffracted. So if there are multiple such layers which are present, then there will be multiple waves which will get diffracted. So now if multiple waves will get diffracted, then their intensities will increase if there will be greater number of such layers. So when we say constructive interference, we means that both the waves, they are in phase. So if both the waves are in phase, that means their crests are overlapping and their trough are also overlapping. So the directionality is same. So in that case, the means resultant wave, it will increase. So its intensity will also increase. So in this way, that is known as constructive interference. Whereas if both the waves, they are different in their phases. So in that case, the amplitude of the resultant wave, that will also decrease. So that will be a destructive interference. So this is to show you that how whenever these are the two waves. So in this I have fixed one wave so that we can compare it. So whenever the second wave, which is coming from that diffraction, if its points are aligning well with the points of the means previous wave, then it will lead to a constructive interference. That means both have the peaks at the same position. So in that way, there will be constructive interference in which the resultant wave will have the highest amplitude. Whereas if they are different in their phases, that means their points are not overlapping. So in that case, the intensity of these waves will cancel out the effect of each other and it will be a destructive interference. So for us to view the proper diffraction pattern, we want to see the constructive interference, and which is also given by the Bragg's law. So later we'll look into the Bragg's law, but before that, firstly we'll understand that what the diffraction pattern means. So there are key aspects of this diffraction pattern. So here is the diffraction pattern. So image plates, they are circular and the intensity readings follows a circular pattern. Because these plates are circular, so that's why we see the diffraction pattern in a circular form. After that data acquisition, the image is erased using the fluorescent light, which also follows a circular motion. And the readout time for this is typically 5 to 7 minutes. So this was also discussed in the course that whenever you are using the goniometer and you are means aligning the crystal in different angles. So for each of that angle, there will be readout time will vary. So depending on how many rotations or movements you are doing, so it will change the readout time. But typically it ranges from 5 to 7 minutes for a particular angle. So image from a R-axis, which is the Rigaku imaging plate detector. So it is a detector which is capturing your diffracted X-rays and producing the pattern. So this detector is a square shaped. So this one is the R-axis detector, which is square in shape. So it results in a higher resolution in the corners. And the primary resolution limit is determined by the radius along the vertical and the horizontal axis. So the detector is capturing your diffraction data, diffraction spots, and the maximum resolution is obtained at the corners. So the intensity values, so means from the diffraction pattern, we get the intensity value. So zooming into the diffraction pattern reveals these intensity values. So here you can see that if intensity is high, then you will see there will be a darker spot. If intensity will be low, then there will be a means lighter spots, light gray in color. So this is how it tells you about the intensity of each of that diffracted wave. And then in certain cases, you might observe certain red spots. So what these red spots mean? So these indicates the overloads. So there is certain limit, certain peak value which can be captured. If your intensity exceeds that value, then it will be an overload. It won't be captured. So in such cases, these spots will appear red in color. And now how it is reported. So in this case, I have used the MOS film to show you that how the intensities are captured for an X-ray diffraction data. So in this case, these overloads, they are represented by special characters such as ampersands. So these and symbols, they are called as ampersands. So there will be 6 such ampersands, and this is to show you that if we zoom out, then this is how it is represented. So in this case, certain squares have the values. These are the intensity values. Whereas in some places, we will see these ampersands, which means that their intensity values exceeds the normal limit of the detector, due to which we are not able to capture them. And their intensity value will be appeared as these special characters. So, I means why it happens? So these diffraction spots, they are generally assumed to follow a Gaussian intensity distribution. That means there will be a peak, and on left and right sides there will be a lower intensity values. But if the peak intensity is too high, that means it is maxed out, the top of the curve flattens. So in this case, because we are not able to capture, we are not able to go to that extent where that peak value rises. So that's why we will not be able to get that point. That's why the peak will flatten and making the accurate intensity determination impossible. So overloads reflections leads to incorrect intensity measurements, which can negatively impact the structure determinations. So this is how means these red spots can means these show that there are overloads in our data, and this also complicates to analyze the structure information for those proteins where the maximum overloads are present. Then there is another term which is indexing. So this was also discussed in the previous session, that what indexing means. So this is the first step. So after the X-ray diffraction data is obtained, so what we do is we perform indexing. So indexing is a tool which determines the best lattice fit for a point group. So after getting that diffraction data, it identifies that what will be the best lattice fit. So we have discussed about 14 Brevis lattices. So by indexing, we try to find out that which one is the best lattice for our data. So it prints the closest real fit and the ideal space group restrictions. And then there is a term in this indexing which is known as tensor index, which measures the fit correlation. So in this case, as you can see, these are the names of 14 Brevis lattices. So from that, diffraction pattern is trying to check out that what should be the ideal unit cell present in the crystal. So in this way, it gives the tensor index value. So this is the metric tensor distortion index. So in this case, the value is given. So we want a value which should be the least among them. So least tensor distortion index represents the best lattice, which will be means occupied by that crystal. So in this, there are 14 fundamental unit cell types, and the program finds the best match. So indexing is a program which is trying to find the best match, and the metric tensor distortion index, its lower value indicates a better fit. So 0.00% of distortion, which is shown for the primitive triclinic, it means it is a perfect match. So the data, the X-ray crystallography data which we have obtained, so that diffraction pattern, so it will best fit for the primitive triclinic unit cell. So this is how indexing works. And now let's talk about the Bragg's law of X-ray diffraction. So according to Bragg's equation, which is the n lambda is equals to 2d sine theta, where n represents the order of reflection, d is the spacing of two planes, and theta is the Bragg's angle. So this angle is the angle which is between the plane and the incident wave which is coming. So that angle made by the incident beam or incident wave on the plane is the Bragg's angle. So according to Bragg's law, the key points are that incident, normal and diffracted beams, they are coplanar. That means they are lying on the same plane. So this is the incident wave, and this is the wave which is getting diffracted, and these all lattice points are present on a single plane. Then diffraction angle is 2 theta. So the diffraction angle is the one which is made between the incident beam, if we extend this incident beam, and the diffracted beam. So this is known as the diffraction angle, the angle between the incident beam, incident wave, and the diffracted wave. Whereas the angle which is made by this incident wave on the plane, that is known as Bragg's angle, which will be theta. And then sine theta should be less than or equals to 1. So in this case, lambda will be less than 2d. And visible light, it cannot be used since the wavelength is too large. So that's why we have moved to X-rays, because their wavelength is of the same size of that of these protein molecules. So for if you want to observe any molecule, then the wavelength should be in that range. So that's why we use X-rays. And this is also the representation for the Bragg's law only. So Bragg's law says that for the constructive interference, the n lambda should be equals to 2d sine theta. Now how this is calculated? So this is the incident wave which is coming, and this is, for example, let's call it as the plane 1, and this is the plane 2. So now the waves are coming in, means they are parallel to each other. They are striking on the atoms present on these two planes, and then they are getting diffracted. So the distance traveled by the wave 2 will be slightly greater than the wave 1, which is striking on plane 1. So we are trying to find out that extra distance, because our aim is to find the spacing of the atoms present among the crystal. So for that spacing, we have to find this distance which is extra traveled by the wave 2. So that extra distance is this one. So for the simplicity, let's look at the figure number 2, which means illustrates properly. So in this case, the extra distance which is traveled is the CB and BD. So rest other distances are exactly identical among wave 1 and wave 2, but the extra distance is traveled by this wave 1, that is CB and BD. So now we have to find the distance, this distance. So if we add up them, so the CB is equals to d sine theta. So according to the formula, as we know that sine theta is equals to perpendicular over hypotenuse, and in this case, this one d, so this d represents the hypotenuse, and BC is the perpendicular. So in this case, this BC will be equals to d sine theta if we means put this into that equation. And similarly, BD will also be equals to d sine theta. So in this way, the extra distance which is traveled by the wave. So now, because there are two waves, so this is 2 lambda. So in this case, n is equals to 2, and the n lambda is equals to 2d sine theta because we will be adding these two extra distances. So with this, n lambda is equals to 2d sine theta. So this is how this Bragg's law is derived from the waves which is striking on two different planes. But what will happen if these waves are striking on a single plane or the adjacent lattice points? Because previously we were looking at two different points which were present on two different planes. But if we want to find the distance between the two atoms present in a single plane, then how we'll do that? So in this case, the X-rays are incident at angle theta on the lattice plane and scatter from the adjacent points A and B. So these are 2 points, and these are two waves which are striking on these points. So constructive interference will occur if the distance, that is AC and DB, are equal. So then it will be a constructive interference. That means there is no phase shift. The angle is exactly the same. So the scattered wave must have the same angle theta with the plane as the incident wave. So in this case, we have to find the distance AC and BD, because rest other distance traveled by these two waves are identical. They only vary in this distance, which is AC by this wave and DB by the second wave which is coming. So the diffracted wave appears as if it is reflected from the plane. So in this, this is the wave X and this is the wave Y. So this is to show you what a constructive interference means. So if both of them, if they are superimposable, that means each of these points are, means their peaks are towards the same direction, then there will be a constructive interference because these two waves will add up. But in this scenario, because they are present in different phases, that means this wave is positive, its amplitude is high, whereas its amplitude is negative. So in this way, positive and negative amplitude, when we sum them, then they will cancel out each other. So in this way, the wave which is obtained, it will be a straight line, which is a destructive interference. Because in this case, the resultant wave, it loses its amplitude. So the amplitude is decreased. So that's why this is known as destructive interference. So our aim is to get the constructive interference. So for this case, when the points are present on the same plane, then the distance, the angle should be equal, as well as the distance traveled by both of these waves, that should also be equal. So in that way, they will generate a constructive interference. Now we'll talk about the Laue's equation. So in Laue's equation, as we know that if we talk about a unit cell, then it has, because in 3 dimensions, it has 3 sides, A, B, and C, and 3 angles, alpha, beta, and gamma. So let A, B, C be the primitive vectors of the crystal lattice L, whose atoms are located at points. So there are 3 axes, X, Y, and Z. So similarly, the points which are located towards direction X, that will be the sum of PA, QB, and RC, that are the integer linear combinations of the primitive vectors. So PQR are the constants and ABC are the these vectors, which are also known as the base vectors. Now, if you consider K in, so K in is the wave which is coming, which is hitting it. So K in be the wave vector of the incoming beam, and K out be the wave vector of the outgoing beams. So which is getting diffracted out, that is the K out. Then the difference vector becomes, so what is the difference between the K in and K out? So that difference will be delta K, which is K out minus K in. So means how the wave vectors are varying. So that is known as their difference. And this is also called as scattering vector or the transferred wave vector. And it measures the change between the two wave vectors. So this delta K, it will identify the difference, that what is the difference between the incoming wave vector and the outgoing wave vector. So the 3 conditions that the scattering vector, which is delta K, must satisfy. So according to Laue's equation, these are the conditions which must be satisfied by the scattering vector. And in this case, H, K, L are the Miller indices, which must be integers. So A dot delta K, should be equals to 2 pi by 2 pi h. Similarly, B dot delta K should also be equals to 2 pi K, and C dot delta K is equals to 2 pi L. So where H, K and L are the Miller indices, and each choice of the integers H, K, L, which are called Miller indices, determines a scattering vector. So this is scattering vector for each of A, B and C, because we have discussed there are three vectors, three directions. So in this way, for each direction, there will be some wave which is coming. K in and K out will exist for these three A, B, C positions. So that's why we have for three different vectors, we will have different scattering vectors for each of these. Hence, there are infinitely many scattering vectors that are possible because HKL can have infinite values. So depending on that, we can also observe different or infinite number of these scattering vectors, which will form a lattice L star, which is also known as reciprocal lattice of the crystal lattice. So what we observe by X-ray diffraction, that is a reciprocal lattice. That's why we identify these HKL, which are the Miller indices, which are reciprocal to the what are actually present on the normal crystal, which is real space. Yeah, so in this case also, AB minus CD will be equals to A cos alpha n minus cos alpha naught, that will be equals to nx lambda. So this is just to find the difference, that is what is the difference between these two waves. So as we have seen in the previous case also, that whenever the this X-rays are striking on any atom which are present on the adjacent adjacent points or adjacent lattice points, then we try to find out what is the position. So to find the distance between those 2 points in the X-ray diffraction pattern, we are just trying to find out what is the extra distance which is traveled by either one of those waves. So to find it, if we want to observe a coherent, or you can say if we want to see a constructive interference, then the distance traveled by the angle at which the waves are getting diffracted, that should also be equal. And we also look for the distance that is traveled by extra traveled by one of the waves, so that we can find out the distance between those 2 points. So in this case, the extra distance traveled by this wave is AB, and in this case it is CD. So this is the difference between them. So that's why we are subtracting AB minus CD, and according to this, because this forms a parallelogram shape, so if we apply this mathematical formula, then the calculation will give us, in the end, we'll get the nx lambda. So now we'll look into the relationship between the Laue's equation and Bragg's law, that how both of them are related. So in the real space, we have a crystal structure and crystal lattice as well as unit cells. So this represents the real crystal or real space, in which we have the x-axis, y-axis and z-axis as well. Whereas in reciprocal space, which is the diffraction pattern when we obtain it, so it is a reciprocal space in which we have x prime, y prime as well as z prime if it is three-dimensional, and it contains the structure factor. So in the later slides, we'll see what is structure factor, what is phase. But in real space, we have the unit cell content. So if G is equals to HA, KB, and LC, which is a reciprocal lattice vector, we know by definition of the reciprocal lattice basis vector that G dot X will be equals to G dot. So in the previous slide, as we have seen, this X, which is a vector, which was equals to PA, QB, and RC. So these ABC were the vectors, and PQR are the constants which are applied to these vectors. So in this way, we add that value in this case for Gx. So this will be PA plus QB plus RC, and then which will be equals to HA plus KB plus LC dot product. So G is equals to HA, KB and LC. So we will put the value of G here, and X value we have also taken from the previous equation. So we will perform the dot product of them. So we perform their dot product. So in the previous slide only, we have seen that A dot del K was equals to 2 pi h. So in this case, uh, this capital A, which will be the reciprocal position for that A, because in the previous case we have small a, but now in the diffraction pattern we have a capital A, which is the reciprocal of small a. So if we put those values, if we means put the value of capital A here, then the equation will become 2 pi into HP plus KQ plus LR, which will be equals to 2 pi N, because this HP plus kq plus lr, it is a constant term. So we have replaced it with n, where n is an integer, which is used. So we use the definition for a reciprocal lattice vector, which gives the factor of 2 pi. So that's why means this is how it is derived. Now the interesting point is that this is nothing but the Laue's equation. So delta k, which we discussed in the previous case, which is the difference between the incoming wave vector and the outgoing wave vector, so which is equals to g. That's why which is also called the Laue's equation. So in the sense of diffraction pattern, they are way for the experimentally measuring the reciprocal lattice points. So in diffraction pattern, we get reciprocal lattice. So for any point x, which we have seen in the previous case, which is the vector, so which is equals to PA plus QB plus RC. So we have del K dot x. So in this case, we have G dot x. So as we know from this equation that del K is equals to G. So if we replace G with del K, so del K dot x will be equals to del K dot, we will put the value of x, which is PA plus QB plus RC, which will be equals to, so if we further means put the values of del k also, then after solving this equation, we'll get p2 pi h plus q2 pi k plus r2 pi l. And if we further solve it, we take the 2 pi constant, then inside it we get hp plus kq plus lr. So these terms will add up, and these are also some integer value which will be a constant. So in this way, we replace this with the n. So n is just an integer which is representing that whatever value we get, it will be the product of means 2 pi. So it will be a factor of 2 pi only. So that's why we replace it with n. So which shows that del k dot h is equals to 2 pi n, and which is also equals to g dot x. So where n is the integer, which is replacing the term hp plus kq plus lr, where hk, l are the Miller indices, and pq are some constant terms which are written to that. So if we further rewrite this condition, so in this case, now we are replacing del k with k out minus k in, because that is the main formula. So why we are doing it? So in this case, we have also seen that del kx is equals to gx. So if we cancel out this x term, then it means del k is equals to g. So g is a reciprocal lattice vector. So now in this case, we are changing del k with the k out minus k in. So in this case, which is equals to g, and if we further square them, so now by changing the direction, k in square equals to g minus. So now this minus term will become positive if it goes to this direction, and g will become negative if it will come to the left side. So in this way, by rearranging them, we get k in square is equals to k out minus g square. So why we are performing these functions or these calculations? Because we want to find the relationship between Laue's equation and Bragg's law. That's why we are doing these rearrangements and doing the square and all these things. So by performing the square, we'll get k in square, and this a minus b whole square will be equals to a square minus 2ab plus b square. So similarly, applying that formula, we get k out square minus 2k out dot g plus g square. So where g is the lattice vector, and whenever it is written inside these, means this is the absolute value, which means it will always be positive. So that's why these are kept inside the two bars, which means these are absolute value. So applying the elastic scattering condition. So according to elastic scattering condition, it says that whatever wave is coming in, it is means reflected by the same value. So k in will be equals to k out. There is no loss. So if we apply this condition, then it will, that means k in and k out are exactly equal, so they will cancel out each other. Now we are left with 2k out dot g will be equals to g square. So this is obtained after rearranging this. So minus 2k out dot g has gone to the left side and it has become positive, which is equals to g square, which is the square of the our reciprocal lattice vector. So essentially, the Laue condition is the conservation of momentum. So the elastic condition is the conservation of energy, which is carried by the X-rays. That is, crystal gains no energy from scattering radiations. So if we apply that condition, so since the angle between the K out and G is pi by 2 minus theta, so because according to Laue's condition, the k in and k out vector, which is passing in, so it forms the isosceles triangle. So if it is isosceles triangle and this is the angle theta, so this particular angle will be equals to 90 minus theta. So 90 is written as pi by 2. So it is pi by 2 minus theta, which is the angle made between this G, which is also called del K, and the K. So, which is K out. So K is K out and K0 is the K in. This is this the representation. So this angle is pi by 2 minus theta. So if we put this value into the term to find the dot product, so when we find the dot product of anything, then we need the dot product is the product of the magnitudes and the angle formed between those two vectors. So in this case, the magnitude is k out for k out vector, magnitude is g for this particular g value, and in dot product, we also need to find the cos angle. So in this case, we have cos, and the angle which is formed between these two vectors is pi by 2 minus theta, which is 90 minus theta. And now cos 90 minus theta is equals to sine theta. So now k out dot g, the magnitude of k out and g, and dot sine theta is coming from this cos pi by 2 minus theta. So now we got this equation. So now we have this already available equation, which is k out dot g is equals to g square. So now we will replace this value which we obtained after performing the dot product of k out and g. So we will put this value here, which will be 2k out g sine theta, which is equals to g square. So since this k out is equals to 2 pi by lambda and g is equals to 2 pi n by d. So in this case, means these values are coming from the previous equations which we have solved so far. So g dot x, we have also checked that it was 2 pi n, where n was the bigger combination of the Miller indices and the so HP plus KQ plus LR. So that is n. And for simplicity, we have written n. And lattice constant is d. So if we put these values into the equation, then we get 2 into 2 pi by theta, which is k out, and then 2 pi n by d sine theta, which is equals to 2 pi n by d square. So we have put value of k out, g and g square here. And with this, if we further solve it, we get 2d sine theta is equals to n lambda, which means that we are now arrived to Bragg's law by using the Laue's equation. So this is how we have identified the relationship between the Bragg's law and the Laue's equation. So this was a bit complicated. So if we go through this 2-3 times, then we'll be able to understand. So there are certain mathematical terms which are present. So means don't worry for now, because means in the exams you won't be asked about this. But before moving further, I'll just confirm that whether it was clear till now. Okay, so I just quickly again means go through this Laue's equation. So in Laue's equation, normally primitive vector has plane A, B, and C. And with A, B, C, we have three different axes, which is x-axis, y-axis, and z-axis. So for each axis, these values A, B, C, it will be there will be a linear combination of these vectors at each point. So that's why for this vector x, we have obtained a linear combination of primitive vectors, which will be PA, QB, and RC. And then we have checked that the incident wave which is coming K in, and there is a wave which is getting diffracted, which is K out. So according to Laue's condition, this del K is equals to K out minus K in, which is known as the scattering vector. And by performing the means to satisfy the Laue's condition, the dot product of A, B, C with del K, it should be equals to 2 pi H and 2 pi K for B and 2 pi L for C, because these are the Miller indices, and this is the scattering vector, and these are the unit vectors which were present in the primitive cell. So this will result in this particular after diffraction. These will be the values which we will obtain because they will be in the form of reciprocal lattice space. That's why we have Miller indices in them. And further, we have looked into the reciprocal lattice vector, which is G, because ultimately in this equation, we are looking for the vectors. So vectors are the quantities which tell you about the magnitude as well as the direction. So in this case, G will be which is the reciprocal lattice vector. By definition, it is the uh, reciprocal lattice vector. That's why we have added the A, B, and C. So these are the HKL are the Miller indices, and capital A, capital B, capital C. These are the vectors present in the reciprocal lattice. So normal lattice, which is the crystal lattice, we have the vectors as small a, small b, small c. But in this case, we will have the reciprocal vectors, which will be capital A, capital B, and capital C. And by changing these values with the previous case where we have looked for the value of x, so that x vector will be the sum of the linear combinations of pk, pa, qb, and rc, which we have seen. So what we are doing in, we are putting those values into these equations, and ultimately we obtained the function 2 pi n. So after putting all these values, we get 2 pi n. So in this case, n is the hp, k, q, lr, because there some will give you some integer value only. So that's why to simplify it, we have replaced it with n. And then we have also observed that del k is equals to k out minus k in, which is equals to g, because in the previous section we have seen that if we resolve it, then del k is equals to 2 pi n. So that's why in g, or g dot x is also coming out to be 2 pi n. That's why we are calling del k is equals to g. And after putting the value, so means we have looked into the g dot x. So similarly for del k dot x, we will find the value. So del k dot x is also coming out to be 2 pi n. So now del k dot x and g dot x are same. That's why we are calling del k is equals to g. And then k out minus k in value will be put, and g value will also be put. So before putting it, we are performing the square of both the sides, which is giving us this particular equation. Now, if there is elastic scattering, so in Laue's equation, according to Laue's condition, there is the elastic scattering. That means nothing is lost during this scattering, during diffraction. So that's why, according to it, the k out and the k in, so both the waves, they should have equal values. So if we put that condition, then we'll get 2k out dot g is equals to g square, because this k in and k out will cancel each other. So from here only this equation we have derived. Now what we are doing is that, because we have seen that the angle, because we want to find the dot product, and dot product between two vectors is equals to, means product of their magnitude as well as the angle which is formed between these two vectors. So in this case, the angle between the k out and g will be this one. So because this is forming an isosceles triangle according to Laue's equation, because it forms isosceles triangle, so both these sides are equal. So this angle will be equals to 90 minus theta. So which is pi by 2 minus theta. So in this way, we have obtained the value of this dot product, which will come out to be this one. So now we are just replacing these values. We are putting these values into the equation, and after performing the calculations, in the end, we observe that it is coming out to be the Bragg's law. So we have reached to Bragg's law, which is 2d sine theta is equals to n lambda. So this is how, with the Laue's equation, we have arrived to Bragg's law. And then we'll look into the real and the reciprocal lattice vectors. So the real lattice vectors, which are present in the unit cell, which is present in the real crystals, and the reciprocal lattice vectors are the ones which we have observed after diffraction pattern. So diffraction pattern provides us the reciprocal lattice vectors. So we need to perform the transformation to get into the real vectors. So in this case, the reciprocal lattice vector, which is H, they are the integer combinations of reciprocal basis vectors. So which will be A star, B star, and C star. And this arrow means these are the vectors, because these are also telling us about the directions in which they are present. These are the basis vectors for the reciprocal lattice, and H is the reciprocal lattice vectors. So this H will be equals to HA star plus KB star plus LC star. So where HKL, which is written after this summation, so which is written in this case, they are the Miller indices, whereas the H which is shown here, which is the reciprocal lattice vector. So it has nothing to do with the Miller indices. So don't get confused. This is just for the notation. They have taken H. So the reciprocal lattice vector will be the sum of Miller indices and the basis vector. So in the previous slides also we have seen the same. For example, in this case, as we have seen, H, capital A, capital B, capital C. So these capital A, capital B, and capital C, they are nothing. They are the reciprocal basis vectors. So here we are representing them with the A star, just to distinguish them with the real vectors. So real basis vectors, which are A, B, and C. So if we perform the derivation, so according to this, they have shown that this particular B B star vector, it is perpendicular to the face AC. So where A and C is present, this is perpendicular to this axis. So if we find the dot product of B star with the A, which is this one, so you can see that it is pointing here towards here. So whenever we find the dot product, it is always the product of the magnitude of B and A plus, sorry, multiply by cos theta. So theta is the angle made between these two vectors. So since in this case, in the reciprocal lattice, the angle which is made between this B star with A is equals to 90 degrees. So because it is perpendicular, so if we further perform their dot product, so it will come out to be BA cos 90 degrees. So cos 90 degrees is 0. So according to that, if we apply the orthogonality property, so the dot product of B star A will be turn out to be 0. And similarly for C also, with C plane also it is perpendicular, so that's why it will be equals to 0. Similarly, this particular C, it is perpendicular to B and A, so it will also, their dot product will also be 0. So which means in the reciprocal lattice vector, B star is perpendicular to AC face of the real space unit cell, which is face normal. Similarly, the other two reciprocal base vectors, they will also be perpendicular to the other 2 points. And in this way, the dot product will be 0. So ultimately, what is the relationship between the reciprocal basis vector and the real basis vectors? So A vector, which is A star vector present in the reciprocal lattice, which will be equals to the cross product of B and C vectors present in the real space divided by the V. V is the volume of the unit cell. And similarly, B star vector will also be equals to C into A by V, and C star vector will be cross product of A vector into B vector by V. So this is the relationship between the reciprocal basis vectors and the real basis vectors. And each reciprocal vector is perpendicular to the real space plane formed by the two vectors. As we have seen in case of B star, it is perpendicular to C and A. Similarly, C will be perpendicular to A and B, and similarly, A will also be further perpendicular to C and B. So now we'll talk about the Ewald sphere. So according to Laue's condition, there are three vectors. So whenever the incident beam is coming, so incident beam, this is which is represented by minus k naught, or which is also known as, which is also represented by s naught, and the wave which is getting diffracted, it is represented by s or k in some case or k out in other case. So, and this one is the reciprocal lattice vector, which is represented by h. In some cases, you have seen it as delta k. In some cases, we have also written it as g, because we have seen del k is equals to g. So there are different notations which are used to represent them. So they must form the isosceles triangle. This also we have seen according to Laue's condition. So with which del k is equals to k in minus k out, which will be equals to h. And how the Ewald sphere is constructed. So in this case, to construct a Ewald sphere, its center will be the point which is the origin of S naught. So this particular center point will be the center point of the Ewald sphere with the radius S naught. So this S naught will be its radius. Now we will construct a sphere or a circle in which so now when the diffraction conditions will be satisfied, if this endpoint of the reciprocal lattice vector h, so if the endpoint of this vector it lies on the surface of this sphere, then only there will be the diffraction conditions. And if it does not satisfy this condition, then in that case the diffraction condition will not be followed and we will not be able to observe the diffraction pattern. So diffraction beam directions, they are determined by the vector s, and by rotating the reciprocal lattice relative to S naught, new reciprocal lattice vectors H that intersect the sphere produce diffraction. So in this case, because the crystal is mounted on the goniometer and we are continuously rotating it at different angles, so each time the direction of this H will also change, and because this H is the resultant vector which is drawn between the S naught and Sk. So this is the difference between the incoming beam and the outgoing beam. So as we are changing the angles, so the direction of this particular H, which is del K, that can also change. So in that way, each time that will change. So each time we will see that whether it will follow the conditions such that it can construct the Ewald sphere or not. So the conditions for Ewald sphere is a reciprocal lattice vector produces a diffracted beam only if the lattice orientation allows H to cut the Ewald sphere. So only then the diffraction pattern will be observed. Otherwise, that wave will escape and we will not be able to observe the diffraction pattern. This means that for a monochromatic beam, the crystal must be rotated to obtain different diffraction peaks. So that's why we need multiple angle rotations so that we can measure the diffraction pattern from different directions so that we can reconstruct the structure of that particular crystal, because in certain cases where this edge will not be striking or not be hitting the surface of the eval sphere, so that particular wave, that particular diffraction pattern won't be observed. So this is the condition for the eval sphere. So main things which you should remember about the Laue condition is that its center point will be the point of, or which will be the origin of S naught, from where the S naught has originated, and the H, which will be the means this lattice vector, it should be cutting the sphere at some point. So in this case, it is cutting this terminal point of the sphere. So that's why it will perform it will give the diffraction pattern. And this diffracted beam, so which is obtained by extending the incident beam, and it is means so from where the reciprocal this vector we have constructed, so from here only we will construct this S. So we have moved this particular diffracted beam to this particular position from where the H is constructed, and now this will tell you the direction, in which direction the diffracted beam will go and make a diffraction pattern. So after talking about the Ewald sphere, there are certain things which we get from the X-ray crystallography data. So first thing is structural factors and the electron density in crystallography. So our ultimate aim from the X-ray crystallography is to get the structure of the crystal, structure of the protein for which we are performing it. So how we can get to that structure? So for that, we need to find out the electron density function, which is rho xyz. So the maxima of this rho xyz, it corresponds to the atomic positions, revealing the internal crystal structure. So with the electron density function, we are able to see that how the atoms are arranged and in which positions the density is higher, in which position atoms are present in greater density, and where the atoms are sparse. So this is the electron density function which tell you that. And then comes the structure factors, which is FHKL. So structure factors are represented by FHKL, which represents the diffracted waves recorded on a detector. The diffraction pattern consists of well-defined spots. So in this case, these well-defined spots are the diffraction pattern, which corresponds to HKL values, where HKL are the Miller indices. So mathematical representation is FHKL is expressed as a vector with two properties. So there are two properties of this structure factor. First is the amplitude, which determines the intensity of the diffraction spot. And second thing is the phase, which is phi HKL, which is the angle of the vector relative to a reference axis. So in this case, what is phase and what is amplitude? So for example, for this wave, the amplitude is the in its peak, so which will tell you the intensity value. So this is the normal plane, and from here we will calculate the amplitude. So this amplitude is the what is the distance, or you can say what is the peak of that particular wave. So that value tells you about the amplitude, whereas how it has moved, so its translational relationship is told by the phase shift. So how means with which angle it has shifted. So that is known as phase shift. So the structural factor, it tells you about both these things, amplitude as well as the phase. So for example, here it has shown that this is the diffracted beam, which is diffracted with some intensity value, which is the amplitude. So intensity is the square of amplitude. So in this way, this particular value is the amplitude, and the angle, which is this phi HKL, which will tell you about the phase, that at what angle it is scattered. These two informations are very important to find the electron density function for a particular crystal which you are observing. So in this way, the rho xyz, which is the real space or direct space, which will be equals to 1 by v, where v is the volume of the unit cell, and this is the summation from negative infinity to positive infinity, because we have seen that for a particular unit cell or for a particular crystal, all the points, they are means they remain fixed. They are the repeating units, so they can go into means they can be present in the infinite directions. So on both sides there are infinite lattice points. So that's why we are summing it on the minus infinity to plus infinity. So it depends that how many such lattice points are present in your crystal. So that's why that value will be, I mean, this value will be substituted with those number of atoms present in the unit cell. So in this case, it will be 1 by V, and summation of from negative infinity to plus infinity for the HKL, which are the different Miller indices. This represents the amplitude, which is the FHKL, and the dot E. And this particular equation, this negative pi HKL, it represents the phases. So this is the reciprocal space. So now this is how the real space and the reciprocal space are related. And we can convert them into each other by using the Fourier transform. So Fourier transform is the method with which we can convert the real space vectors into the reciprocal space and vice versa. So this is reversible thing. And this is the formula which shows that how, if you have the real space, then how you can identify the reciprocal space, because by X-ray diffraction, we get the values of the reciprocal space. So from that reciprocal space, how we can go back to the electron density function and identify that how in the structure of the protein, how the atoms are distributed. So this equation tells you about that, and you don't have to worry about the complicated equation. For just, this is just for the understanding. So you must only know this thing, that there is the amplitude and the phase information which is captured from the reciprocal space and which is generally required to get the data of the real space or the direct space. So now we will look little bit detail into the structure factors. So what is the definition of structure factor? So it represents the resultant of all the scattered waves in the direction of a given HKL reflection. Because we have seen that a single molecule was insufficient to get a proper detectable X-ray diffraction pattern. So that's why we need multiple unit cells or multiple such molecules. So now if multiple molecules are present, so all of them, all those planes and all those atoms, they all will diffract the X-rays. And now all those diffracted X-rays, if they are in phase, then they will combine together. Those waves will be merged and they will give a intensity, which will be the resultant intensity, which will be greater than the individual intensity of each unit cell or each unit plane. So now that's why the resultant of all those scattered waves in the direction of given HKL, which will be the structure factor. So in this case, all those lattice points will determine that what will be the structure factor. So it is expressed as FHKL equals to F1, F2. So this is just representing the number of such atoms which are present. So it is simply the summation for J number of atoms present in the particular crystal, and E I pi. So this is the simplistic representation. Otherwise, if we expand it, then it will be the F Fj. So in this case, it is Fj, which is the electronic property of an atom. And we'll also discuss that what it means. So it is the atomic scattering factor. So means how much the X-ray will be scattered, and it depends on the, means what it is. It does not depend on the position of that atom, but it depends that what is that atom, what is the electronic distribution of that atom. So for example, if we have carbon, then it has the electronic, it has the atomic number of 6. So in this case, it has 6 electrons. So the F value or the scattering factor will be 6 at the value of sine theta by lambda. When sine theta by lambda is equals to 0, then the atomic scattering factor is equals to 6. So always remember this thing, that whenever the sine theta to lambda is equals to 0, so in that case, the atomic scattering will be equals to the number of electrons present in that particular atom. So that's why it will decrease as the sine theta upon lambda increases. Yeah, so FHKL, the structure vector, it is the electronic property of an atom and the structure property or the position of that atom. So it is the dot product of these two terms and summing them on the number of such atoms which are present. So which will give you the structure factors. And in the previous slide, we have seen that structure factor is the combination of amplitude as well as the phases. And why we need it? So that we can get into the electron density map and we can understand that how the atoms are arranged in the real space. So this is the structure factor and this is the atomic scattering factor. So whenever this sine theta by lambda equals to 0, so in such cases Fj will be equals to total number of electrons in the atom, and Fj decreases as the sine theta by lambda increases. Because what is happening? Due to reduced scattering efficiency at the higher angles. because if there is higher angle, then the scattering efficiency is reduced. That's why the scattering is also reducing. So this atomic scattering factor is also reducing with increased value of sine theta by lambda, because sine theta angle is increasing. So protein components and scattering. So that's why, because in carbon, nitrogen, oxygen, which are major constituents of proteins, so they have nearly similar number of electrons. There's not much variation. So they only vary by 1 or 2 electrons only. So which leads to the comparable scattering behavior. So that's why there is not much difference in the intensity values or the scattering values among these atoms. And then comes the phase. So because we have discussed the structure factor, next thing is the phase. So phase difference in the Bragg's law. So according to Bragg's law, the phase difference between two reflected. So in this case, we have two different beams. One is red beam and other one is the blue beam. So the, means the phase difference between the two reflected red beams or two reflected blue beams will always be 0 degrees or 360 degrees, that is 2 pi radians. So in this case, if we have two red beams, then the angle between those two red beams will be 0 degrees. So means there is no phase difference. Sorry, the phase difference will be 0 degrees. That means they will be the angle at which they are reflecting or they are diffracting the X-ray beam, that will be identical. There will be no such difference. So in this way, both the K out coming from these two planes of the red beams, they will show a constructive interference. So that means del phi will be equals to 2 pi radians. 2 pi radians means 0 degrees or 360 degrees. So pi means 180 degree and 2 into 180 degrees 360. So that's why del phi for the red beam will be 2 pi. Similarly, for these two blue beams, it will be 2 pi. That means there is no such phase difference between these two beams. And this means that the wave scattered from atoms in the same lattice plane remains in phase. So these are the same lattice planes, because there is one lattice which is formed by the red beams. So they're because these are the same lattice planes, so their waves will also be in phase. That's why they are 2 pi. And now what will happen? So what is the phase difference between the red beam and the blue beam? So for that will be the del phi, which is the phase difference, because these two are the different lattice planes. So that's why the angle at which they are diffracting, that might vary. So for that, to identify that particular angle, we are finding the difference between the phases of both these waves. So del phi represents the difference between the phases or the phase angles between these two beams. So which will be equals to phi 1 minus phi 2. So phi 1 is the individual phase of uh, this red beam, and phi 2 is the individual phase of the blue beam. So phase shift due to lattice separation, because they are separate, their distance will also be different. So in this case, BK is the vertical distance between this red beam, and A by H is the horizontal distance between this red beam, so two planes of the red beam. So if there is a separation between two lattices, as in the case of two atomic layers, a phase shift arises between the red and blue scattered waves, and this phase shift reduces the total diffracted intensity because the waves do not add up perfectly in phase. So, for example, in this case, because these two beams, if there is some shift in the phase, if they are not exactly in phase, these two waves will not be in phase, then there will not be a constructive interference. Because if we add both the phases, so if we add both these phases, so there will be a negative effect if they are not properly in phase. So it will not sum up perfectly. So which will not be a proper constructive interference. So using the proportionality relationships for these three independent crystallographic directions. So from this particular red lattice point, there could be three possible directions, because we have three different axes, and to identify the position of this particular lattice point, which will be present on certain point in the x-axis, y-axis, and z-axis. So this represents the x, y, and z-axis where it is present. So the phase difference, because means this particular point is it's represented by x, y, and z planes, as well as by the base vectors, which is a, b, and c, as well as the hkl, which are the Miller indices. So for the particular crystal lattice, whenever we are representing that particular point, we need to use all these vectors to show that point. So in this case, A by H equals to 2 pi, B by K is equals to 2 pi, and C by L will also be equals to 2 pi. So why is it 2 pi? Because we have seen that this particular phase difference is equals to 2 pi. And the H will be equals to del phi A, Y is equals to del phi B, and Z is equals to del phi C. And del phi is the phase difference between these two beams. And now similarly, if we put the formula, so del phi A will be equals to 2 pi hx by A. Similarly, del phi B is equals to 2 pi ky by B. And similarly, del phi C is equals to 2 pi lz by C. So this is just means we are rearranging it and putting all the values. So this is how we will get um, del phi A, del phi B, and del phi C. So this is the phase difference among these three different directions, A, B, and C. And if we sum up the contributions from all these three directions, so it will come out to be phi del phi. So this is del phi A plus del phi B plus del phi C. So if we sum up them, so 2 pi will be a constant, or you can say this is the common term among these three. So it is taken out. And then hx by A plus ky by B plus lz by C. So we will add these values. So which will tell us the, means what is the phase difference among these two beams. So what is the that difference? So that we can find out that whether it will lead to a constructive interference or destructive interference, what will be the intensity. Because our ultimate aim is to increase the intensity so that we can observe the better diffraction patterns. So this is to check that, means if there are two separate atoms and two separate lattice vectors or lattice planes which are present, so how it will impact the intensity of the X-ray beam which is getting diffracted. So to check this, we are finding out the phase difference among these two diffracted beams. So in fractional coordinates, x is equals to capital XA, y is equals to capital YB, and z equals to capital ZC. So now in this case, A, B, C are the constant terms. So we can simply, if we ignore them, then small x will be equals to capital X, small y will be equals to capital Y, and z will be equals to capital Z. So if we replace it in this equation, then we get pi is equals to 2 pi by 2 pi square, means parenthesis hx plus ky plus lz. So this tells you that what is the phase. So the phase factor is crucial in determining the interference patterns and structure factors in crystallography, because this will tell you that what will be the intensity, how will the diffraction pattern vary, and means, so for that calculations we must need the phase value. This is how the phase value is calculated, and this shows that why the phase value is important. So again, I'll say the same thing, that you don't have to worry about these equations which are given. You just need to get through the basics, that why we need the calculations, why we need the phase values, and what is the aim for identifying the structure factor and phase value. So the structure factor, which was FHKL, it represents the total scattered amplitude from the atoms in a unit cell. Because if there are multiple atoms, then there will be multiple scattered such X-ray beams, and those all X-ray beams, their waves will be sum up and it will form a single spot. So that single spot, that will be its position will be calculated, and it will depend on the what is the intensity of those X-ray beams which are coming out. So if F1 corresponds to the dispersion of the red atoms, because in this we have seen there are two separate layers. So one was by the atom red and another was by the blue atoms. So they have separate planes from where these X-ray beams are getting diffracted. So if F1 is corresponding to the diffracted wave, diffracted X-ray beam by the red atoms, and F2 corresponds to the dispersion of the blue atoms. So this one is the F1 beam and this one is the F2. So they have separate angles at which they are diffracting this X-ray beam. So for example, F1 is diffracted at the angle of phi I, whereas F2 is scattering at the angle of phi 2. So now, because in the end, the wave or the pattern which we get, which will be the combination of where the two waves will be combined. So in that way, we have to find the resultant wave, that what will be the resultant of this particular wave. So in this case, the resultant will be this particular FHKL, because it is summing both of them, both of these, it is merging both these waves. So in this way, the resultant wave is FHKL, and we want to find this structure factor. So now this FHKL will be F1 plus F2 because it will sum both these waves. So now vector sum of the scattered amplitudes. So the magnitude of the vector sum is given by. So now how we will calculate this FHKL? So FHKL is the sum of two vectors F1 and F2. And according to mathematics, how we can sum two vectors? We need to sum their uh, means both the axes. So x-axis component is also summed and y-axis component is also summed. So in this case, F1 has the x-axis component as F1 cos phi 1 and its y-axis component is F1 sin phi 1. So in this case, F1 cos phi 1 as well as F1 sin phi 1 is written, which is added. Similarly, for F2 also, we will add its x-axis as well as y-axis components. So x-axis component is F2 cos phi 2, whereas y-axis component is F2 sin phi 2. And we will sum them. We will perform the square of x-axis component as well as y-axis component and add them and then calculate their square root. And why we are calculating their square root? Because FHKL, which is the magnitude or which is the amplitude, so it is the square root of the intensity. So intensity is the square of amplitude. So that's why we have to perform this square root. So this tells you about the what will be the resultant amplitude which will be generated by these two waves. So these are the individual amplitudes and this is the resultant amplitude. So this is why we need the calculation of the phase value as well as the intensities. So now phase of structure factor. So in the previous equation we have only seen the structure factor. Now how we will find the phase angle? So phase angle is equals to tan inverse of f1 sin phi 1 plus f2 sin phi 2 divided by f1 cos phi 1 plus f2 cos phi 2. So this is simply the relationship between the sine and cos phi, which will tell us the tan phi. So calculation of phi. So this is simply using the trigonometric functions. So we are simply dividing x-axis and y-axis component to get the tan phi. So tan phi is equals to sine phi over cos phi. So similarly, tan is going to this direction. That's why it is getting inverse. So phi is equals to tan inverse and summing up means summing up the x-axis component and dividing it with the y-axis components. So sine phi 1 by the cos phi 1 and similarly sine phi 2 cos phi 2. So this is how the phase of the structure factor is calculated. Now, if we generalize it to the all atoms in the unit cell, so this one is simply for some atom F1. But what if there are multiple atoms? So in such scenario, we have to add the all those atoms because whenever we get the diffraction pattern, then it's not just the product of a single atom or two atoms. There are multiple atoms present in the unit cell, and then in the crystal lattice, multiple unit cells. So all those atoms will scatter the X-ray beams, or you can say diffract the X-ray beams in some particular order. So we need to combine all of them to get the structure factor. So in this way, for example, if there are J such atoms in the unit cell, so we need to sum it up for all those J elements. So this is simply doing the same thing for the J number of elements. So this equation is written in this form to generalize it for the J number of atoms. And the corresponding phase will be phi will be equals to 2 pi hx plus ky plus lz radians. So where hkl are the Miller indices and xyz are the simple those directions, those vectors means uh, real or the real space vectors. So these are the h, y, and z. And in this case, they have not written it in detail. So we can also write it in detail if we add the means PA plus QB plus RC. So means if we put those values in XYZ, so in that way we can also calculate it. So this is just for simplicity. They are represented by HX, KY, and LZ. So this formulation is crucial in X-ray crystallography, where the structure factor determines the intensity as well as the phase of the diffracted waves, and ultimately it will help us to reconstruct the atomic structures. So from the diffracted pattern, we can further get the how it is originally present in the real crystal. So for that, we need this information. And if we means write it in the complex forms, so in the complex form, this particular axis is the imaginary axis and this is the real axis. So in the real axis, which is the x-axis, we have the value of A as f cos phi, and in the imaginary axis, it is the f sin phi. So in the previous also, we have seen the x-axis component as well as the y-axis component. So similarly, the magnitude is obtained by the Pythagoras theorem. So if we want to find this FHKL, so this this is the perpendicular and this is the base. So by Pythagoras theorem, the hypotenuse square will be equals to base square plus this perpendicular square. So FHKL will be equals to square root of a square plus b square, and phi will be tan inverse of b by a. So the structure factor, which is FHKL, it is represented using the complex numbers to define both the magnitude and phase. So the general formula will be this one. So this we have already seen in the previous case where we are generalizing it for the j number of atoms. So we will sum all those Fj cos phi for H, Xj, Kyj and Lzj, and we'll square it. We will add both the x-axis component and the y-axis component, perform their square, and then ultimately their square root, because this value is the intensity value, whereas FHKL is the amplitude. So intensity is the square of amplitude. That's why we need to square root it. And the phase is given by the tan inverse, and then uh, means summing up all the y-axis component to the x-axis components. So sine thing is the imaginary axis component, whereas cos is the real axis component. So these equations are as same as which we have discussed in the previous slide only, but written in some other way. Okay, so now for the complex number representation, in this case, that equation, same equation which we have seen here, so it can also be represented as FHKL is equals to square root of j 1 to n fj cos 2 pi hxj kyi and kyj and lzj plus I, and then this sign thing is written. So now why we are rewriting it in this form? So that we can convert it using the Euler's formula, so that we can represent it in the shorter form. So by using the Euler's formula, which says that EIX can also be represented as cos x plus I sin x. So in this case, we already have cos, this whole term will enter into x, and plus I sin and this x term. So to write it in a simplistic form, we can also write FHKL as summation ji to n fj, and now instead of this whole term, we are replacing it with EIX. So in this case, E is written as same, I will also be the same, whereas x is the 2 pi hxj plus kyj plus lzj, which is constant term in both these cos and sine. So now this is the simplistic form with which we can represent the structure factor. And this is how the real and imaginary axes, how they are formed. So the complex formulation is fundamental in crystallography and Fourier analysis because it allows the direct calculation of diffraction intensities and phases which are necessary for the electron density reconstruction. Because if greater is the intensity, which means that the waves which are coming, first of all, it will tell you that there are multiple such waves. And second thing, it will tell you that because intensity is increasing, that means these waves are in phase. So with the help of phase information and the intensity information, we can reconstruct the electron density maps, which will ultimately tell us that how the atoms are arranged inside the protein, because our ultimate aim is to visualize the structure of proteins. So this shows that why we need the structure factor as well as phase information. And then why we need Fourier transformation. So Fourier transformation is the ultimate player which is helping us to convert the reciprocal lattice space to the real space. So structure factor and its role, which is FHKL. So this equation we have already seen. It represents the contribution of atoms in the unit cell to the scattered X-ray waves. So whatever we observe, the structure factor is telling us that relationship, and it contains both amplitude as well as phase information. And when we talk about the electron density function, so this is the real on the real crystal. Structure factor is observed for the reciprocal lattice vector, which is the which is coming from the diffracted data, whereas electron density function, which is lying on the real crystal. So in the real crystal, how the electron are distributed, how the atoms are arranged, that is known as electron density function. So to obtain this, we need to perform the inverse Fourier transform. So inverse Fourier transform to convert the structure factor into the electron density function. So now this is how the electron density towards x, y, and z axis is calculated. It is the 1 by v, v is the unit cell volume, summation over HKL for FHKL is the structural component, and then by using both the phase information and the amplitude, the structure factor is represented by this equation. So phi HKL is the phase of the structure factor, FHKL is the amplitude of the structure factor, and V is the unit cell. So this is how electron density function and structure factor are related, and this is simply the Fourier transformation. So with the help of Fourier transformation of structure factor and this amplitude, we are getting to the electron density function. And now why we need Fourier transform? So X-ray diffraction results in the overlapping waves from multiple lattice planes, which makes it difficult to analyze the individual atomic contributions. So for that, we need Fourier transform, which will decompose these waves, which are the resultant waves, into the individual component frequencies, their amplitudes, and their phases. So with which we will be able to know the atomic densities. So how those individual atoms are distributed. So that's why we need Fourier transform. And how it helps, so there are different lattice spacings which produce distinct diffraction patterns. So performing the inverse Fourier transform reconstructs the crystal's electron density. So it will tell you that how the different atoms, how they are distributed. So their individual amplitudes and phases information will be provided by the Fourier transform. So with which we can construct the electron density map, and ultimately we will be able to know the 3D structure of the molecule. So in this diagram, it is showing that this is the complex signal, which is shown by the red wave, which is broken into the sinusoidal components, which is the colored curves. So this single wave is broken into three different individual components. And these summation of these waves, which is giving us this particular resultant wave. So till now we have seen that how the waves coming from multiple planes and then separate atoms, they are ultimately combined and then their intensities are calculated. So in this case, by Fourier transformation, we are further dividing it into the individual components so that we can know that how these atoms are arranged. Yeah, so this is just another representation that how the electron density as well as the structure factors, they are involved. These are their equations, and with the help of Fourier transform, we can convert electron density to the structure factor as well as structure factor to the electron density. So this is interconvertible. So from crystal we can convert to diffraction pattern, and from diffraction pattern we can get the 3D lattice in the crystal. So this is just for that sake only. Now comes the phase problem. So now phase is very important, but how to find that angle, how to find the phase? So structure factor is given by this equation, which is FHKL is equals to summation over J number of atoms, FHKL, which is amplitude, and e raised to power minus 2 pi I pi, where this pi is the phase angle. So this is the amplitude, this is the phase, and both are essential because if we want to find the electron density map, then we need both these informations. But how the phase problem arises? So whenever we find the X-ray diffraction pattern, we can measure the intensities, which are IHKL, which is proportional to the square of structure factor amplitude. So when we say this amplitude FHKL, this is the square root of IHKL. So that means intensity is the square of this amplitude. So with this, we can identify this amplitude by with the help of intensities of these points. We can calculate the amplitudes, but how to find the phase? So phase information is lost during the measurement. And why? Because to reconstruct the electron density functions, we need both the amplitude and phase, because we also want to see at what angle. Then only it will define that whether these intensities are adding up, or means how the intensities are influenced by the waves which are coming. So for that, we need the phase information. So since phase data cannot be directly measured, so which creates the phase problem. Yeah, so this is to show you that how the phase problem arises. So this diagram shows that these are the individual atoms which are present. So now whenever the X-ray will come, they will diffract that X-ray at some angle. So that is at some phase, or you can say that at some angle. So now how to find the phase angle? So the magnitude of this resultant wave is measurable, but the phase angle of its components, that is unknown. So without the phase information, we cannot accurately reconstruct the atomic structures. So in this case, the resultant amplitude. So these are the separate means waves, or separate at separate amplitudes, this particular wave is getting diffracted. So the resultant wave is calculated as the wave which close, because if we place these waves in the sequential order, then the resultant wave will be the one which will close this particular form or close the structure. So this is the resultant wave which will be the summation of the amplitude of all these waves, but it is telling you the resultant wave. It will tell you about the amplitude of the waves which are getting deflected by all these atoms, but somewhere we are not getting the information that at what angle each of these atoms are reflecting this X-ray wave. So for that, means we need to solve this phase problem. So if you want to understand the electron density function, so that electron density function is the 1 over V and summation. So in the previous slide, we have written as summation HKL. So this can also be written as separate summation over three different Miller indices, HKL, and then this FHKL is the amplitude, and then exponential. So in some slides, you might see that it is written as E raised to power minus 2 pi I HX KY LZ plus I phi HKL. So these are different ways to represent it, but this is the same equation which we have seen earlier. So which is showing the relationship between the electron density function and the structure factor. So where FHKL was the amplitude, phi HKL is the phase which is missing in the experimental data, V is the unit cell, and HKL are the Miller indices. So their calculation also we have seen in the previous session. So what data do we collect? So by the diffraction pattern, we collect the position data, intensity data, and the key relationship also we have seen that intensity is square of the amplitude. So which means that with the intensity values, we are able to get the amplitude, but we are not able to get the phase, which leads to the phase problem. So now how to solve this phase problem? Yeah, so this is another thing that by performing the Fourier transform, for example, if we have a single atom, then the Fourier space will be the broad and smooth function in which we are, means because this is a single atom, so we do not get the proper diffraction pattern. But if there will be a crystal, then it will transform into a diffraction pattern which will consist of discrete spots. So now in this case, after performing Fourier transformation of this particular crystal, we get separate dots, which are the discrete spots. So this shows you that we need, first of all, this tells you that we need a crystal for getting a proper diffraction spots. And single atom is not sufficient enough to produce a diffraction pattern. Yeah, so now this is to how to solve the phase problem. So there are multiple techniques with which we can solve the phase problem, with which we are able to tell that how our two atoms, means whether how much there is how much separation between those two atoms present in a protein molecule, so that we can construct the structural components of that particular protein. So we need to solve this phase problem. So there is a Peterson function given by the scientist. So he said that if, because this is applied only on the small molecules, and in that case we can solve this equation, we can identify the electron density map even in the absence of the phase information. So this information may be accessed by the calculation of Peterson function. And how we get the Peterson function? So it is obtained by calculating a map using a squared structure factor magnitudes in which all the phases are set to 0. So in this case, we simply replace the phase value by 0. So we do not consider this phase information and we are simply relying on the amplitude information. So instead of peaks at the atomic positions, Peterson map shows the peaks at every position that corresponds to interatomic vectors in the structure. So in the previous case, we were looking for the individual atomic positions, but in this case, the values which we are getting, that will be the simply the interatomic spaces. So this approach becomes usable for the structures of this approach will be unusable if the structure is more than 50 atoms. So it is only reliable till the 20 to 50 atoms. That means if there is a small molecule. So this is the Peterson function formula, which is PUVW. So in the previous case, where we were looking at rho XYZ, so here only I have shown. So rho XYZ. So XYZ, these are three different directions. So for an individual point, these are three different axes. So x, y, z represents the position of that particular atom. But in this case, in Peterson function, we have UVW. So UVW is not telling you the location of an individual point. It is telling you the interatomic distance. So how much the my atom 1 is, means how far it lies from atom 2 in the three different directions. So in the next slide, we'll see that how the UVW are linked to the XYZ. So Peterson function is equals to 1 by V, similar thing which we have seen previously. So summation HKL over the FHKL square. Now in this case, we have replaced the amplitude with the intensity. So which is the diffraction intensity and which is the square of this amplitude, and cos 2 pi HU, KV and LW. So in this case, we are only considering this uh, cos 2 pi, which is the real axis and not the imaginary axis, which includes the sine component into it. So in this case, because we are uh, means making the phase value to be 0, so that's why the phase is not captured. So we are only having this cos 2 pi value, which is obtained after solving this particular equation. So because by using Euler's formula, EIX is equals to cos x plus I sin x. So in this case, because the phases information is not required, we are turning it to 0. So we have lost this I sin x. We only have EIX to cos x, so which is written here. So the x value is replaced with 2 pi HU plus KV plus LW. And in this UVW are similarly the interatomic distances. Instead of using the individual positions, which were x, y, z, we are using the interatomic distance information, and amplitude is replaced with the intensity. So this is the difference between the electron density function and the Petersen function. By using this function, we no longer require the phase information if our molecule is sufficiently small. Yeah, so this is how the XYZ is different from the UVW. So UVW will tell you the distance between these 2 points. For example, this is my atom 1, this is my atom 2, and this red line, the red arrow, it represents the distance between these 2 points. So this will be U. So U will be means this distance will be present in 3 different space because 3D coordinates are present. So to represent this distance, we need to represent it with 3 different coordinate values. So U will be x1 minus x2 towards the x-axis. V will be y1 minus y2. So it is telling you the interatomic distance towards the y-axis, and similarly W is the interatomic distance towards the z-axis. So which is z1 minus z2. So this is how in Petersen we get the value of UVW, which is the interatomic distances. So information provided by the maxima of Petersen function corresponds to the map of position vectors, which is the relative positions. So keep this thing in mind that in this case, instead of XYZ, we have UVW, which are the uh, interatomic distances. The value of the function at these maxima is proportional to the product of implied atomic numbers. So with this, also keep this thing in mind that if the atomic number is greater, then it will give the higher value of Petersen function. And Petersen function is depending on the intensities, because in this we have seen that Petersen function is equals to summation of the intensity values. So which means if atomic number is higher, then this value will also increase, which means intensity will also increase. So which provides the clear advantage for detecting the vectors. And in this case, because the heavy atoms will have greater number of atoms or greater number of electrons, so they will increase the value of Petersen function. So with this, we can use the heavy atoms to get the means to perform this. So in that case, we do not need the phase values. With the heavy atoms, we can increase the Petersen function values. So suppose a crystal space is defined by the value rho function at every point in the unit cell given by the coordinates x, y, and z. So Petersen space is defined by the generic coordinates UVW, which is the difference between the coordinate of each pair of atoms in the crystal. And this is just the another way. So if there are n atoms, so in that case, how many such interatomic distances will be there? That will be n square. So for example, if there are 4 atoms, then we are finding the distance of atom 1 with 2, 3, 4, and with itself as well. So that's why it is written as n square. But if we remove the self component or the self distance, then it will become n square minus n. So this is telling you how many interatomic distances are possible and how the number of atoms will tell you the how many possible such means interatomic distances or interatomic vectors are possible. So that will be n square minus n, which is much reasonable. And then there is another property of Petersen function, which means that if there is a vector from atom 1 to 2, so in this case, this is atom 2 and this is also atom 2. So this particular red bar, which is telling you the interatomic distance, so they are saying that this interatomic distance from atom 1 to 2 is equal to distance between atom 2 to 1. But only there is difference in the direction. So which means that this Peterson function is always centrosymmetric. There is no variation even if we calculate the distance from atom 2 to 1 or 1 to 2, there is only change in the directionality. But otherwise it is identical. The distance is the same, which means it is centrosymmetric from and towards both the directions. Now the next method to resolve is, so Peterson function, by using Peterson function, it comes under the direct method. Now the next method is by introduction of the heavy atoms, which is also known as isomorphous replacement. Now this heavy atom replacement, if there are multiple such heavy atoms which are used, then it comes under multiple isomorphous replacement. If we only use a single heavy atom, then it comes under single isomorphous replacement. And for the protein crystals, how we can perform this heavy atom introduction into the crystal. So for this, we need to soak the crystal in the heavy atom solution, or we can also perform the co-crystallization. So whenever we are means making the protein crystals, at that stage also we can add the heavy atom. So in that way, they can co-crystallize. These are two ways with which we can introduce the heavy atoms into our protein crystal. And now this method is also known as isomorphous replacement. So isomorphous means that it should not influence the structure, or it should not influence the geometry of that particular unit cell. So for that thing, we need to keep this thing in mind, that our heavy atom should not alter the crystal formation or the unit cell dimensions. So in that way, because the structure will remain same, that's why it is known as isomorphic replacement, because it is not interfering with our structure of the crystal. So modified structure factor will be FPH. So previously it was FP, which means the structure factor by the protein. Now FH is the structure factor by the heavy atom. Now if we combine both of them, then it will be the combined structure factor by both the protein and heavy atom, because ultimately both of the amplitude of these waves will combine. So we are simply combining these vectors, and which will be the FPH. This is the modified structure factor, and this particular figure is telling you that we have the protein crystal, which is KOMS2, and now we are adding the ruthenium, which is the heavy atom. So ruthenium is being added. Ruthenium is represented with Ru, and Mn is the manganese. So this manganese is replaced with ruthenium at certain positions, and because ruthenium has the higher atomic number, which means it has greater number of electrons. So because we have seen in the previous slides also that if the atomic numbers are great, then it will have the higher scattering, and heavy atom incorporation will increase the scattering intensities, which will lead to a modified structure factor. So in this way, manganese is replaced with ruthenium in this case, and this is known as isomorphous replacement. Okay, so now the problem, if we only use the single, if we perform single isomorphous replacement, for example, in the previous case, we have only used ruthenium. So now the problem with a single isomorphous replacement is that we are not sure about the which phase to choose, whether to choose this particular phase of, or whether to choose the this particular phase for the resultant FPH. So in that case, there arises the phase ambiguity problem. So to solve this, we need the multiple isomorphous replacement, because single isomorphous replacement makes it bit confusing to choose the direction. So with multiple isomorphous replacement, in this case, we have the resultant means vector given by the heavy atom 1 as well as resultant vector given by heavy atom 2. So now with this, we are very sure that what will be the resultant FP by this particular protein. So what will be the directionality? So this helps us to resolve the phase ambiguity problem. So in this way, we need the multiple isomorphous replacement for dealing with the phase ambiguity problem, because previously there are two different possibilities of two different phases towards the positive axis as well as negative axis. So now in this case, because we are using two different heavy atoms, so now this will tell us the true phase angle, true phase value. So now this is telling you that by using MIR, we have now a single phase, and which is also having the higher peak, whereas in this case there are two separate peaks, two separate possibilities of the phase angles. So this is the advantage of using the multiple isomorphous replacement over the single isomorphous replacement. Okay, the similar thing is shown here as well, that this is the protein with the heavy atoms, and this is the normal protein, and these are the heavy atoms. So now this is just to tell you that how it brings about the difference in the diffraction pattern. So two protein diffraction patterns shifted vertically. So in this case, if we superimpose both the diffraction patterns, if we compare them, firstly without the introduction of heavy atoms and then by introducing the heavy atoms, so now this shows the vertical shift relative to one another. So one is from the native protein and other is from the crystal of the same protein, which is soaked in the heavy atom solution, which is mercury in this case. So intensity changes for the reflection in the later because we are introducing Hg, so the intensity value will increase comparatively. And identical unit cells, in this case the unit cells remain identical, which means that this is there is the maintenance of isomorphism. So Hg is not changing the geometry or arrangement of the crystal lattice. So by performing the calculations, they have mentioned that by if we add one mercury atom to the protein of 1000 atoms, then it will produce an average fractional change of intensity by the 25%. So differences should be easy to measure. So with this, it tells you that how heavy atom replacement can change the intensity values. So for example, if we add only a single mercury atom, then the intensity value is increased by 25%. So similarly, there is a formula with which we can calculate the relationship that what will be the change in the intensity factor, that is del F, and F is the normal amplitude of the previous native protein intensity. So this tells you the difference which the heavy atom is bringing. So ZH and Z effective are the atomic numbers of heavy atoms and average of the protein atoms. So Z effective is the average atomic number of the protein, because in protein there are multiple atoms. So we will combine their atomic numbers, which will be Z effective. ZH will be the atomic number of the heavy atoms, and the square root of 2NH. That means NH is the number of heavy atoms which you are using, and NP is the number of protein atoms. So how many atoms are present in the protein? So this equation will tell you that what will be the difference in the intensity factor which will be brought about the introduction of heavy atoms. So with this you can calculate, you can identify that how much heavy atoms you should use to bring about the change in the intensity values. Now the next thing is anomalous dispersion. So this is also the factor. So what anomalous dispersion means, that if the incident X-ray radiations has a frequency close to the natural oscillation frequencies of the electrons, then there occurs the anomalous dispersion, which will modify the atomic dispersion factor, which was Fj, or also represented by F naught. So in this situation, the expression of scattering factor is modified with two terms, which is F prime and F double prime. So F will not be equals to F naught. It will also be including the F prime and F double prime factors. So what is happening, if there is the high energy X-ray beam which is coming, which has the potential to uh, means just knock out the electron from the inner shell to the outer shell to 5s, then in some scenarios what can happen is that this extra energy might get absorbed. So there might be change in the this particular, because this F prime and F double prime factor might add, so which represents the real and imaginary components of the anomalous fraction of atomic scattering. So anomalous dispersion means if there is change in the phases of the beams which are getting diffracted, sometimes due to absorption, there might be change in the phase of those X-ray diffracted beams, so which leads to the anomalous dispersion. So in protein crystallography, anomalous scattering refers to change in the diffracted X-ray phase that is unique from the rest of the atoms in a crystal due to strong X-ray absorbance. So if there is absorbance, then it can lead to change in the phase values. So relative light atoms found in proteins such as carbon, nitrogen, and oxygens, they do not contribute to anomalous scattering at normal X-ray wavelengths used for X-ray crystallography. So thus, in order to observe the anomalous scattering, there must be a heavy atom which is present and which should be native to a protein, or a heavy atom derivative which should be made such that it does not interfere with the protein structure. So in addition, the X-rays wavelength should be close to the heavy atom's absorption edge. So in such scenarios, we will observe the anomalous dispersion. So in this case, the example is taken of the selenium atom. So in selenium atom, which is a heavy atom example and which can easily be achieved for the protein. So in the next slide, we'll see that. So what will happen is that there will be a breakdown of Friedel's law. So according to Friedel's law, the intensity of HKL and minus H minus K minus L reflections, they are equal. So, but in this case, if there is anomalous dispersion, if there is an anomalous scatterer, so selenium is the anomalous scatterer if it is present. So, because it has the ability to absorb the X-rays, so in some of the atoms of selenium, they can absorb the X-ray and there will be change in the angles with which it is diffracting that X-ray which is striking on it. So, with which what can happen is now the FKH will not be equals to F minus H minus K and minus L. So which will break down our Friedel's law. So according to Friedel's law, these both should be equal. But now, because of the presence of anomalous scatterer, it is now absorbing the X-rays, and now this will not be equal. So FKH will not be equals to F minus H minus K and minus L, which is known as anomalous dispersion. Similarly, in this case, delta F is largest when the contribution from F naught uh, contribution F naught from the anomalous scattering atoms is pi by 2, that is out of phase with that of the non-anomalous atoms. So in the protein, we will have both the anomalous and non-anomalous. So anomalous are the ones which are heavy atoms and non-anomalous are the ones which are the other atoms of the protein. So if the contribution of delta F will be highest, if the angle means the delta F is largest when the contribution F naught from the anomalous scattering atoms is pi by 2 out of phase. So if it is pi by 2 out of phase with that of non-anomalous atoms, then delta F will be largest. Whereas if delta H will be smallest when the F naught contribution is in phase with that of the non-anomalous atoms. So it depends that how that non-anomalous is scattering that X-ray wave. So if it is in phase, then delta F will be smallest, whereas if it is out of phase, then delta F value will be largest. Okay, so now the concept of this anomalous dispersion can be used to solve the phase problem, so which is known as multiple anomalous dispersion. So its mechanism is that because the inner electrons, they absorb X-rays of specific wavelength and re-emit them with the delay, including a phase shift in all the reflections. This is known as anomalous dispersion effect, as we have discussed. So in this case, the selenium is the one which is absorbing the X-rays, and then this is absorbing some of them. So there will be the change, there will be a shift of phase. So the angle with which it was diffracting for other atoms, so that might change because of the absorption. So phase shift analysis. So the induced phase shift varies for different reflections, and analyzing these shifts will help us to solve the phase problem. Yeah, so this is to represent the phase shift of anomalous scatterer. So this one is the imaginary part of the anomalous scatterer, and this one is the real part of the anomalous scatterer. So we have to find the resultant phase shift by this particular. So the angle will be the beta. Angle means the phase shift which has happened is means mentioned with the angle beta. Earlier it was alpha or phi, but now it is beta. So what is the requirement for this multiple anomalous dispersion? So the requirement is that we should have the anomalously scattering atom which should be present in the protein structure. So now how we can introduce this means anomalous scattering atom. So in methionine we have sulfur because we want to perform the replacement in such a way that it does not interfere with the geometry. So in that case, we should be very much confident enough that it does not change the protein. So in this case, in selenomethionine, we simply replace the sulfur with selenium. So it will give rise to selenomethionine. In this way, we have added the heavy atom into the protein structure or protein crystal. And with this, if we compare the normal crystal with this particular crystal where we have inserted the heavy atom, so we will be able to find the differences. So proteins without the natural anomalous scatterer can be expressed in equali in the medium containing selenomethionine, and then selenium atoms will serve as the anomalous scatterers for X-ray crystallography. So this is how we are inserting the selenium into the particular amino acid present in the protein. And ultimately, because it is the anomalous diffractor, or it will lead to, it is the anomalous scatterer, so there will be some variations which it will bring about in the protein crystal where we have inserted it. So by comparing both those intensity values and the patterns which we are observing, we will be able to get the phase problem. We will be able to identify the distribution of the atoms present in that particular crystal. So this will also help us to solve the phase problem. So even without the information of the phase angles, we will be able to solve this problem with the help of selenium. And to improve the phase, so there are different experimental methods with which we can improve the um, means the distinguish between the phases and the other things. So first thing is the solvent flattening, which removes the negative electron density. So which simply this is the solvent and these are the proteins. So with the help of solvent flattening, we are simply defining the boundaries. We can distinguish among the protein and the solvent. So it removes the negative electron density values so that we can only consider the protein values. So which sets the solvent region to a typical value of 0.33 E by angstrom cube, which is the protein density. And protein density is 0.43 E by angstrom cube. So it uses the automatic methods to define the protein and solvent boundaries. Then comes histogram matching, which is also helping in the phase improvement. So in this case, we adjust the electron density values to align with the expected distribution. So for example, if this is the distribution, electron density distribution from the refined atomic coordinates, and this one is the electron density distribution from the isomorphous replacement phase. So we will simply align them, we will adjust the values in such a way that both of the electron density values align with the expected distribution. So this is known as histogram matching, where we are trying to match them so that we can improve the phase values. Then the third thing is non-crystallographic symmetry averaging. So in this case also, because in a single unit cell, there might be the repeats, similar repeats, and which are varying only in some symmetric functions such as rotations, translations. So this applies the symmetry operations when multiple copies of a molecule exist in a asymmetric unit, and this ensures the equivalence in the electron density values. NCS, which is non-crystallographic symmetry, differs from crystallographic symmetry because it is not periodic. So in this way, by performing the averaging of this non-crystallographic symmetry, we will be able to we will also be able to improve the phase informations. So these are the three methods with which we can improve the phase information by using the prior knowledge. And then the last method, which is most commonly used, is the molecular replacement method. So in this case, means this is the method which is used to determine the structure of unknown protein when the similar known structure exists. So if there is already available some protein structure, so we simply try to find it out. For example, if already means we have a sequence of the new protein for which we want to observe the structure. So we already have some protein already whose structure is available. So we simply check that whether the new protein, whether its sequence is nearly similar to that of already predicted protein structure. So with that, we can simply use the previous information to predict the structure of the new protein. So key principles of this are which requires a previously solved homologous structure. So homologous means they should share some sequence identity among themselves or a lower resolution NMR structure of the same protein. So this uses this known structure to determine the orientation and the position of the unknown structure within the crystal lattice. So this is the example. For example, we have the unknown molecule and this is the known molecule. So by simply performing the rotation of this particular known molecule, we can get the similar structure of that of the unknown molecule. So in this case, we will simply perform some symmetric functions to predict the structure of the unknown molecule if it has some level of sequence similarity, if it is homolog. So there is three-stage process for this molecular replacement. First one is rotation search, so which determines the relative orientation of the unknown structure by comparing it with the known structure. So we are trying to check by performing the rotation, we are trying to check that whether it resembles my unknown protein or not. Then comes translation search. So in this positions the rotated structure correctly within the crystallographic unit cell. And then comes phase determination, which uses the known crystallographic relationships, which are found in step 1 and 2 to calculate the phases for the electron density reconstruction. So for example, in this case, we already have the structure for this particular protein. We will perform the rotations in different directions, and then we will perform the translational search. We will pack them into a unit, these into multiple unit cells and construct a crystal, and then we will perform the refinements. So in this case where we are performing the rotation and translation, we are checking that whether it is aligning well with our unknown protein molecule or not, so that we do not have to perform all these calculations for the unknown protein molecule. If both of them have the homologous sequence, then it is the hypothesis that if two proteins share some sequence identities, then they will likely give rise to a similar structure. So that's why we are using this information of the already available homologous protein structure which is present, and simply performing the rotational and translational searches. And then ultimately, computational aspect is that we perform the 6D search, which is 3D rotation search over all possible orientations, and then 3D translation search to place the oriented model in the unit cell. And then additional steps will include the packing, validation, and refinement to optimize the fit of that model. For example, in this case, by performing this rotation, we got the nearly similar structure to that of our unknown molecule. So this is how we can perform the molecular replacement. And the one main thing is that we need a prior information of the already available structure. And in this, it has been shown that this molecular replacement is a good search model. And according to the molecular replacement, there is a rule of thumb that we can only consider two protein sequences when they share the sequence identity of more than 30%. Then only we can call them as homolog, and then we can continue with the predictions. So where the sequence identity is low, it is important to get a good sequence identity as possible. And then comes signal to noise ratio. So anything that is in your model that is not likely to be in your target structure, such as side chains, flexible loops, so we need to remove them so that we can reduce the noise which is present in our structure, which is already solved. Then collaborative computational project number 4, which is CCP4, which is a institute which develops the software for the macromolecular X-ray crystallography. So there are various programs in this CCP4 which help us to find the good search model with which we can start our search. And then such other program is MolRep, which is also a program which is used for the molecular replacement in the cases where the homologous structure has already been identified. So simply we can use this program to find the number of molecules expected in the asymmetric unit as entered by the users. And this is the representation of that. So these are the different angles, theta, phi, and chi, and then tx, ty, and tz, different coordinate values. So means this tells you that for the molecular replacement, you must have some already solved homologous protein sequence, for which we already have the structure. Then only we can refine it and predict the structure for our current protein sequence which we have. Yeah, now this is the means practical considerations that how we can perform the molecular replacements. So we can use online databases such as FASTA sequence search. For example, if you have a protein sequence, so then how you will be able to know that whether homologous protein sequence exists or not. So for that, we can simply search for the other sequences. So for that, we can use EBI FASTA, or we can also use BLAST. So, or we can also perform the structure-based search. So OCA PDB search is also the another way with which we can perform the search. And then preparing a good search model. So for the good search model, we must have sequence identity value greater than 30% and modify the model to remove the noise. So we can remove the things which are not available in the current sequence for which we want to find out the structure. So we will remove such side chains or some disordered regions or loops which are complicating the analysis. So those things are removed to increase the signal intensities and reducing the noise. Yeah, and these are the examples that what are different tools which are available to perform molecular replacement. And this is the table for the comparison among different methods which we have seen so far, such as direct methods, then single isomorphous replacement, multiple isomorphous replacement, then single anomalous dispersion, then multi-atom anomalous dispersion. And then if we are combining both the anomalous scattering along with the isomorphous replacement, then these are slight high level techniques which are having better refinement. So CIRAS and MIRAS are the combinations of SIR, SAD as well as MIR, MAD. So means just to increase the intensity of the diffracted beams and better distinguish among both the patterns so that we can resolve the phase problem. So these are the techniques with which we can solve the phase problem. Now comes the refinement, because we have obtained the structure factor as well as the phase values. We have dealt with the phase problem. So now After getting those values, we need to refine our model so that we can upload it on the PDV or the structured databases. So for refinement, we can use the rigid body refinement, in which what we do is we search for the global minimum for the target energy function. So this is the energy function E total, which is the sum of W X-ray, which is the weight for the X-ray energy term. E X-ray is the X-ray energy, plus E conformation is the conformation energy terms, and E non-bonded is the non-bonded energy terms, which are coming from the van der Waal and other interactions, electrostatic interactions. So we are simply trying to check that whether the model which we have obtained, whether it has the least energy. So that if it has least energy, which means it is highly stable. So in the refinement, our aim is to get the structure which is the most stable structure, which exists in the wild type form. So that is we are doing in this case. So rigid body refinement means we are fixing the means if it is a multi-domain protein, so we are fixing two domains and we are only allowing a certain region to move. So in this case, the constraint coordinate refinement of one or more group of atoms that each move, rotate and translate as a single body. So these all atoms are rigid. These are fixed. They will move as a single body. So all these atoms can only move at once. As a single body, these individual movements are not happening. Only there are certain atoms present in between which are joining these two groups. They are free to move. So for each group of atoms specified by the user as a rigid body, the three rotational and three translational degrees of freedom are minimized. So with all those rotation and translations, we try to find out that in which of the conformation it is having the least energy value. So that will be our stable conformation. Second refinement method is the positional refinement, in which we will adjust the x, y, and z coordinates of atoms to refine their positions. So the challenges in this positional refinement is that because we have large number of atomic parameters, so it is difficult to perform the individual XYZ coordinate refinement, and then weak diffraction from the macromolecular crystals. So for not all the crystals we get proper diffraction pattern. So that is also the limitation, and then poor ratio of parameters to observations. So this is also one of the problem with positional refinement. Then comes the occupancy refinement. So occupancy represents the fraction of molecules in the crystal where the atoms is found at a specific position. So for example, in this case, if we have a phenylalanine, so these two are representing the occupancy of that phenylalanine uh, for particular time. So it is possible that in this 3D coordinate space, it can have different occupancies, different positions it can occupy at different point of times. So for example, it is possible that for 25% of the time it means it is present in this particular conformation where it is present in this side, whereas for 75% of time it might occupy this particular space. So this tells you about the occupancy. Occupancy means where in the 3D space where it is present for the means for how much time it is present in which space. So which tells you the occupancy factor, which tells you about the movement of the molecule and its conformations, that in which and how many conformations it can exist. So if it has the occupancy of 1, which means that all the molecules are identical, it is occupying a single position, it is not moving here and there, it do not have any other alternate conformation which exists. So for that reason, occupancy factor is important because it tells you about the alternate conformations for that particular molecule present in the protein, that particular atom or group. So refining the occupancies help to estimate the frequency of alternate conformations. So ultimately, this refinement helps to means ensures that the final electron density map which we are getting, which accurately reflects the molecular structure and reducing the errors and ambiguities in the atomic positioning. So this is the main aim of the refinement. And now next thing is the B factor. So now what we are doing is we are trying to refine our model after getting the model from the X-ray diffraction. So B factor is another term. This is also known as the temperature factor. So which describes the atomic motions in the protein structures and are crucial for understanding the flexibility and disorder in the crystallography. So for each protein, we will find out the B factor, which will tell you about the properties of the protein. So means if B factor value will be high, where the electron density is low. So if electron density is low, which means those regions, they are flexible or it might be disordered regions. If B factors are low, so which means that particular region is the well-ordered region in which the atomic positions are in the well order. Then comes ideal protein structures typically have the B factors between range 20 to 30 angstrom square. So this is the typical range. And for mathematical representation, B factor is applied exponentially to the scattering factor, accounting for the thermal motions of the atoms. So B factor FB is equals to Fe raised to power minus B sine theta by lambda square. So we have seen in the previous case that Fj, where we were looking at the atomic scattering, so Fj was proportional to sine theta by lambda, and when sine theta by lambda was equals to 0, so in such case Fj was number of electrons present in that particular atom. So similarly, this is how the B factor is linked to the scattering factor. So there is the exponential relationship between both these terms. And then there is another equation by Debye and Waller which relates the B factor to atomic displacement, where U means the displacement of an atom. So B is equals to 8 pi square U square. So these are some mathematical notations, but the thing which you have to understand from the B factor is that it tells you about the flexibility, that the atoms present in the protein are either they are flexible or either they are rigid, or which are the regions where the flexibility is high, which are the region where flexibility is low. So all those informations can be obtained by finding the B factor. And now this tells about the carbon. So in carbon, as we have discussed previously, that if the sine theta by lambda is 0, so in that case, Fi, the scattering is maximum, which will be 6, which is equals to the atomic number. And as the value of sine theta by lambda is increasing, similarly, there is drop in the scattering. So which shows the effect of B factor on scattering intensities, where the increasing B leads to the decrease in the electron scattering. Now in this case also, these means you can see the B factor is highest for these red lines. So the red line represents the side chain. So this shows that side chains have the highest B values than to the main chain or the all atoms, which means that side chains are flexible enough. And if for the homology modeling also, they have compared the modeled as well as crystal structures. So these regions where the peak is observed for the B factor, which means that these regions means there is some discrepancy, because this much highest peak should not be observed, which means these regions are either intrinsically disordered, or these regions contain the means amino acids which are highly flexible. So this is how the B factor refinement is also important, because if B factor is very, very high, then those regions interfere with the structural interpretation. They do not tell about the proper structure. Then comes R value, which is very important. So R value measures the agreement between the crystallographic model and the experimental X-ray diffraction data. So it tells that whether the refined structure predicts the observed data or not. So if R value is sufficiently high, then only the databases such as PDB will accept your structure. Otherwise, you need to perform more refinements. So R factor is kind of an agreement. And the calculation of R factor is done by the summation of F observed minus F calculated divided by the summation of F observed. So if the R factor is 0.6, which means it is very bad. If it is 0.5, it is bad. If it is 0.4, that means recoverable. So means we need that R factor should be as least as possible. So it should be 0. That means it is perfect. And we do not have to do further refinements. And now how we use these R values. So these are used for the model building and evaluations. So first of all, researchers construct the atomic models of the structure. Then the simulated diffraction pattern is generated from that model. And then R value will measure that how well that simulated pattern matches the experimental data. So in this, by performing the simulations, some structure is modeled, and then the comparison between the crystal structure and the model structure is made. So this is how the model building happens. And then what could be the possible reasons where our simulated model and the crystallographic model means uh, might not be same. So how it can happen? So first thing is water channels, because when you are simulating it, then you have the because you are performing it online in silico, but in reality when you are performing it, so in that case you are using protein crystals. So in protein crystals there are multiple water channels, so due to which means the structure information might vary among both two scenarios. And then comes disorder and vibration. So atomic disorder and vibration can also affect the diffraction, but these are not accounted in case of models where you are using the computational models. So in that case, you are not worried about the disordered and other things which can happen in the real space. So these two things are the reasons why we can see the imperfect fit. And what are the challenges in the interpretation? So the refinement process adjusts the atomic model to better fit the data. And this can also introduce the bias as the refined models is used to calculate the electron densities. So means there is still a biasness which might happen when you are means interpreting the R values. So now there is another method which is the simulated annealing with which you can refine your model. So in simulated annealing, what happens is this is a molecular dynamics method, which is a refinement technique. So in this case, we control the temperature which is linked to the kinetic energy of system. In this, we try to overcome the local minima. So in sometimes we can what can happen is that we are starting from this configuration and we reaches this particular configuration and we feel that this is the global minima, this is the least energy structure, and now we stop here. But in reality, there might be some global minima which has the least energy which is possible. So in such scenarios, we need simulated annealing. So in this case, we try to optimize the protein structure which is stuck in the local minima. So to reach the global minima, we provide some energy. External energy is provided, which push this particular conformation of protein to the higher energy, which crosses this barrier. And now this is also known as the hill climbing. So now it will reach the hill and it can move on both the directions and it will decide that which direction will take it to the least energy state. So in this scenario, it will reach here and this will be the favorable direction of its movement. So if we have to talk about the thermodynamic terms, so the probability of accepting an energy increase is given by this equation. So this is the probability of the energy change will be equals to exponential of minus del E divided by KT. T is the temperature. So higher temperature means there is more frequent acceptance of the bad moves, allowing the exploration. So in this state, it is exploring because this state is the lower energy state, whereas this state is the higher energy state. So for this particular protein structure to move to the higher energy state, we need to provide the external temperature. So if higher temperature is provided, then it can favor the movement to the unfavorable state because this unfavorable state can allow it to explore the other minimas. So in this case, if it reaches here, then there is a possibility that it can find the another local minima and ultimately reach the global minima. So this is the need of the higher temperature. And if there is lower temperature, then the fewer bad moves will be accepted, which will refine the solution. Okay, so the application of simulated annealing in folding is that it assumes that the folded protein structure corresponds to the global energy minimum, and simulating annealing is also helping the atomic model to achieve the most stable conformation. So this is the representation that at initial temperature, our protein structure was here, and now it will move down the energy gradient. It will reach here where the energy is minimum from this case, and now it will not move upward. So to let it move upward, we need to provide some external temperature. And in case of simulated annealing, there is some probability. So if that probability value is higher than certain threshold, then it will climb up the hill and it will ultimately, it will again move on both the directions till it reaches the least energy value, which is the global minima. So as soon as it reaches the least value, then it will not move further, and which will be the point where the temperature will be now lesser temperature. So that will be the final temperature. We will reduce the temperature so that it does not further move to some other positions. So this is how with simulated annealing we can reach to the global minima for that particular protein structure which is stuck at the local minima. And ultimately now performing all those refinements, now because our structure is ready, so we can deposit it to the PDBs. So PDB is a database where the protein structure can be uploaded. It is a single worldwide repository for processing and distribution of 3D biological structure data. So we need to prepare the data, we validate that data. So validation server is designed to check your model and experimental files prior to starting of deposition. So before deposition, we need to validate it. And then there is a tool named as ProCheck, which also accesses the geometry of residues in a given protein structure as compared with the stereochemical parameters from the well-defined high resolution structures. So it also makes sure that the structure which we have given, so that should follow the already available stereochemical parameters. And then after passing through this project, it will be means deposited in the PDB, and further anyone can access that structure. So for a proper or a means the resolution of the protein structure which you are uploading, so it will be good if it is less than 2 angstrom, and R factor should be 20 to 23%. So R factor value should be less, because if it is less, that means your crystal structure as well as the model structure, they are means there is not much difference among them. So in that case, the possibility of acceptance of that particular structure will be higher. So this is all about the today's content. Now we will go through certain MCQs. So today's lecture was quite lengthy because there are many terms which are available. So now we'll quickly go through these questions. The first question is, in X-ray data processing, determining the intensities of each spot is termed as, so option A is indexing, option B is integrating, option C is merging, and option D is none of these. So do you have any idea about the what should be this process where we are determining the intensity of each spot? Okay, now we'll see. So the right answer is integrating. So means if we talk about the first option, which is indexing, so indexing identifies the crystal lattice. So in the initial slides, we have seen that with the help of indexing, we can identify that what will be the proper crystal lattice, and it assigns the Miller indices, which is HKL, to the diffraction spots. So this comes before the intensity determination, whereas integrating, so it measures the intensity of each diffracted spot by summing the recorded X-ray signal in that region. When we talk about merging, so merging combines the multiple intensity measurements of the same reflection to improve the accuracy. So in this way, integrating is the right option because it measures the intensity of each spot. The next question is, which of the following equality must be fulfilled for Laue's condition? So A is S equals to S naught plus H. B option is S equals to S naught minus H. C option is S equals to S naught by H, and D is equals to S equals to S naught into H. Okay, now let's see. So what is the right answer? So the right answer is option A, which is S equals to S naught plus H. So when we were discussing about Laue's condition, and we said that the incident beam, which is the K in or represented by K naught, and the diffracted beam, which is the K out or K. So their resultant vector, which will be formed by these two waves, is H, which is also represented by delta K, which is K in minus K out. So in this scenario, this forms the isosceles triangle, and the H is calculated by finding the difference between the S and S naught. So S minus S naught is equals to H. Similarly, if we rearrange it, then we get S equals to S naught plus H. So in this way, S equals to S naught plus H is the right option, where S naught is the wave vector of the incident X-ray beam, S is the wave vector of the scattered X-ray beam, and H is the reciprocal lattice vector. Now next question is, the Ewald sphere demonstrates the relationship between option A, the wave vector of the incident and the diffracted X-ray beam. Option B is diffraction angle for a given reflection, and option C is reciprocal lattice of the crystal, and option D is all the above. Okay, so now you have to tell that what does Ewald sphere demonstrate among these 4 points. Okay, so now let's quickly see the right answer. So the right answer is all of these. So Ewald sphere tells you about the wave vector of incident and diffracted X-ray beam, so which is S naught, and the S naught is the incident wave vector, and then SHKL is the diffracted wave vector. So there are multiple ways to represent it. In some textbooks, you see it as K in, K out. In others, you see it as S naught S, or you might see it as S naught SHKL. So do not worry about it. So these wave vectors are represented by the Ewald sphere, and then diffraction angle is also represented. So intersection of the reciprocal lattice points with the Ewald sphere determines the which reflections satisfy the diffraction conditions, thus relating to the diffraction angle. So means because it tells you that the H, which is the wave vector transfer, so it should means cut the Ewald sphere at one point, then only the diffraction can happen. So in that way, it is also telling you about the diffraction angle, because we have discussed that because the goniometer is rotating the crystal, so there is a possibility of multiple such H vectors. So with each angle there will be separate h vectors, and then if h vector will cut the Ewald sphere at its top, then only the diffraction can happen. So somehow it is also telling you about the diffraction angle, and then reciprocal lattice of the crystal. So that h is the reciprocal lattice. So that is also means can also be demonstrated by the Ewald sphere. So that's why option D is correct. So now next question is, which of the following obtained the first solution to the phase problem? So option A is Arthur Lindo Patterson, option B is Alexander Fleming, option C is Alexander Alekhine, and option D is William Bragg. So in this question they have asked that who was the following. Okay, so you have mentioned option D. So the right answer is to this is the option A, which is Arthur Lindo Patterson. So when we were talking about the phase problem, so we mentioned that Patterson function was the first way with which we can deal with the phase problem, but this was limited to the small molecules. And why William Bragg is not the right option? Because William Bragg does not tell about the how to deal with the phase problem. He simply worked about the whether the X-ray diffraction pattern will be better or not. So they only told that in which scenarios the X-rays which we have obtained, they will perform the constructive interference. So they have not solved the phase problem. That's why option A is right. Whereas option B says Alexander Fleming, so he discovered penicillin, whereas Alexander Alekhine, so he is the world chess champion, so he has nothing to do with the phase problem. Now question number 5 is, which of the following methods for solving the phase problem requires the prior knowledge of structure of a homologous protein? So option A is direct method, option B is MAD, which is multiple anomalous dispersion, option C is MIR, multiple isomorphous replacement, and option D is molecular replacement. So this also we have already discussed. Okay, now quickly see what is the right answer. So the right answer is option D, which is molecular replacement. And if we talk about direct method, then the Patterson method comes into it, direct method in multi-wavelength anomalous dispersion. So in this case, we have already discussed that in this case, we generally use the selenium or other thing to, means we use the anomalous scatterer molecules, which can absorb the wavelength and bring about change in the phase angles. Then comes multiple isomorphous replacement. So in this also, we use the heavy atoms. Whereas in case of molecular replacement, we need a prior knowledge of the structure of a homologous protein, and then we use that information to predict the structure of the unknown structure, unknown protein molecule. Now the next question is, anomalous dispersion effect is observed in option A molecular replacement, option B is MAD, option C is MIR, and option D is direct method. Okay, so this is also straightforward. So the right option is MAD, which is multi-wavelength anomalous dispersion. So this uses the effect, anomalous dispersion effect, because it uses the molecule which is the either the heavy atom or the anomalous scatter. So in the example we have discussed about the selenium. That's why MAD is the one which uses the anomalous dispersion effect. Next question is, in direct method of solving the phase problem, ab initio phase determination is limited to option A is greater than 1.2 angstrom, option B is greater than 2.2 angstrom, option C is less than 1.2 angstrom, and option D is less than 1.2 nanometers. Okay, so now let's see. So in this case also, the right answer is less than 1.2 angstrom. So during this course, means this week content, sir has also told you that in case of direct methods, there are two things which must be set aside. First thing, that molecule should be small. It should have lesser number of atoms which are present in that molecule. And the second thing is that it should be having the higher resolution. So higher resolution means the lesser value. Higher resolution means when we say great resolution, it means it's the value which is of that resolution should be as low as possible. So in this case, less than 1.2 angstrom, which is known as the ultra high resolution. So this is the condition to solve the phase problem by using the direct method. And the next question is, which of the following is not a classic heavy atom used for isomorphous signal? Option A is mercury, option B is gold, option C is platinum, and option D is uranium. Okay, so now let's see. So the right answer is uranium. Because in case of isomorphous replacement, we generally replace some atoms with the heavy atom. by without bringing about change in the geometry of that unit cell. But in this case, although the uranium is the heavy atom, but it is a radioactive in nature, so we generally skip it and we uses mercury, gold, or platinum. This is not the classic heavy atom because there will be a risk that it can cause many means it can bring, it could be deadly. The people who are dealing with the crystallization, so that's why this is no non-classic heavy atom. Now the next question is, which of the following parameter can be used to search for the number of molecules? Option A, twinning. Option B, number of unit cells in a crystal. Option C, Matthews coefficient. And option D is none of these. Okay, so this thing also we have not discussed. So let me tell you the right answer. So the right answer is Matthews coefficient. And the explanation is that if we talk about twinning, so it refers to the intergrowth of two or more crystal domains and it does not determine the number of molecules. If we talk about number of unit cells, so this only tells you about the unit cells and unit cells contain molecules. So it has nothing to do with the number of molecules which are present. So then it does not directly determine the number of molecules. Whereas if we talk about Matthews coefficient, so which is also represented by Vm, so it is used to measure the number of molecules per asymmetric unit by relating the unit cell volume to molecular weight of the protein. So this is the formula that how the Matthews coefficient is linked with the volume of unit cell and the number of molecules per asymmetric unit and the molecular weight of one molecule. So with this we can calculate the Matthews coefficient, and with if we have the value of Matthews coefficient, then we can calculate the number of molecules which are present per asymmetric unit. So this is how there is a relationship between number of molecules and Matthews coefficient. Now the next question is, in molecular replacement, how much minimum percent sequence identity with the homologue is required? So this is also straightforward. 30%, greater than 30% was the minimum criteria, that it should have at least 30% sequence identity to call it as a homologue and perform the molecular replacement. And now this is the paper in which means these people have mentioned. So after performing different comparisons, they found that if there is at least 35% of sequence identity, so in that case, the molecular replacement has given better results. So in this paper, if you are interested, you can go through this, in which they have discussed that what are the different tips and tricks which we can use to means maximize our results using the molecular replacement method. And then the last question is that if an X-ray of wavelength 60 angstrom is incident on a crystal at an angle of 90 degrees, then what should be the interplanar spacing for the first order diffraction? So the options are these, and this question I have kept because it was also in your assignment. So this is with the slight variation. So how we can solve this? We will use the Bragg's equation for solving this particular question. So in this case, as they have mentioned, it is a first order diffraction. So first order diffraction means n will be equals to 1. So by using the Bragg's law, which is n lambda equals to 2d sine theta, so lambda is the wavelength. So in this case, X-ray wavelength is 60 angstrom. So it is 60 2d sine theta. So angle is 90 degrees. So that will be sine 90 degree, and we need to find the value of d. So 60 equals to 2d sine 90 degree, and we know that sine 90 degree is 1. So we get 60 equals to 2d, and d will be 60 by 2, that is 30 angstrom. So this is how we can find the interplanar spacing, that is the space between two planes, or the d. So this is 30 angstrom. So this is the right option. Okay, so that is all for today's session. Um, Yeah, and I know that today's session was a bit complicated because there were a lot of equations. So do not worry about these equations. You do not have keep these equations into mind. There are certain facts which you must remember, that what are the basic things, that why we are identifying all these structure factors, phase values. So only keep those things in mind. And I hope means I have helped you to resolve the doubts. So if you have any further doubts, then you can means ask your doubts in the discussion forums. So okay, then I'll end the class if you do not have any doubts, and I'll meet you for the next session. So thank you so much. I'm ending the session.